Hello and welcome. Today we're going to talk about the dissolution process. What actually happens when something dissolves? This is covered in the OpenStax chemistry textbook, chapter 11, section 1. So if you want to read a bit more detail, you can check those pages out. All right, so first of all, let's talk about ionic compounds. We have two types of materials that will dissolve, ionic and molecular, or covalent if you want to call it, all right? So when ionic compounds dissolve, like potassium chloride, the ions separate from one another and become solvated by individual water molecules, and that's shown here in this little diagram, okay? So potassium chloride is composed of alternating potassium cations and chloride anions, okay? Purple, green, purple, green, purple, green, all in that lattice, okay? But then when water comes in, it completely surrounds the cations and completely surrounds the anions and takes those off into solution at rather large distances from one another, okay? So remember that oxygen is delta minus, so all the oxygen atoms are going to be pointing towards the cations in the case of K+. This is called an ion-dipole interaction. Remember that in the water molecule, because of the differences in electronegativity of the oxygen-hydrogen bond, the hydrogen is labeled delta plus. And so all the hydrogens are going to be pointing towards the chloride because, you know, opposites attract there, okay? And that also is an ion-dipole interaction. And because we know potassium chloride dissolves in water, apparently water has a stronger affinity for individual ions to break up that ionic bond between the potassium and the chloride ions, okay? Now, in the case of the one thing you want to do is remember that all monoatomic ions dissociate, okay? I have this formula here, magnesium chloride. Magnesium chloride is composed of magnesium ions, shown here in this crazy diagram here in kind of like a tan color, and chloride is shown here in green, okay? Now, MgCl2, you might think, well, there's two chlorines, they're connected or something, but in this diagram, none of the green chlorides are bonded with a line to any other green chloride, okay? They're not bonding to each other. There is no chlorine-chlorine bond in magnesium chloride. So when you dump magnesium chloride into water, it dissolves, and all the water molecules surround each of the magnesium ions. And remember, magnesium is +2, right? Magnesium is +2, it's positive. So the negative part of the water molecules should be surrounding that ion, okay? And if we draw a little diagram of this, it kind of can't really see it well in the diagram. But if we look at this here, we could see, my Avogadro modeling application shows the hydrogen surrounding the magnesium ion, so this doesn't look correct here. But anyway, when you do a space filling diagram, it kind of shows how the water molecules are really surrounding the ion, okay? Whereas if you draw a ball and stick like this, it really doesn't show up as much, okay? So I just wanted to show you the space filling diagram. Water has a huge impact on whether something is going to dissolve or not. So here we have just a simple diagram showing how the magnesium is that tan guy in the middle, and then we have two chlorides, one on the very left, one on the very right. They completely dissociate, okay? So you have two chloride ions there in solution, all right? A lot of students accidentally show this equation on the bottom. Please don't do that. The two here in this balanced chemical equation that shows the dissolution just indicates that you have two chlorides present, okay? It indicates a quantity. It does not indicate a bond. So please don't show this reaction on the bottom where you have magnesium chloride. Well, it's also incorrect because there's no subscript of 2, but showing how that forms magnesium 2+ and then a Cl2 molecule with a negative charge. That has no meaning, okay? Always balance at the end. We'll see some sample problems now. So let's write the dissolution for barium chloride, okay? So barium chloride, when it dissolves, forms barium ion. Look in your periodic table, barium's in group 2, so it has a +2 charge. And then chloride is group 7, okay? It has a -1 charge, so we write Cl-. Then the very last step of this process is to balance the chemical equation. Use the 2 to put a 2 in front of the chloride. We call that a coefficient to balance the chemical equation. How about aluminum bromide? Aluminum bromide, let's see, aluminum is in, well, that's in group 3, so it's +3 in charge. And then bromine is in group 7, so bromide has a charge of -1. Now we use the subscripts in the starting chemical to put a 3 in front of the bromide, okay? Don't put a bromine with the 3 under it, okay? There's no meaning for that. Lithium sulfide. Lithium, let's see, find that in your periodic table. That's in group 1, so that's going to be a +1 charge. And then sulfur is in group 6 of the periodic table, so that has a -2 charge, okay? The last step and final last step is to balance the chemical equation. So we look at the 2 and then we put a 2 in front of the lithiums, okay? Now I want to talk about polyatomic ions. Here's a structure, nitrate. Okay, nitrate is a polyatomic ion that does not dissociate because it's comprised of covalent bonds. Those lines between the red and blue atoms are covalent bonds. So when you add nitrate to water, there's no reaction, okay? It just stays nitrate as an ion floating around. Therefore, when you take sodium nitrate, yes, the sodium ion dissociates from the nitrate ion, but the nitrate ion stays as a unit. Please recognize and maybe even memorize the polyatomic ions that are extremely common. We have a few of them. We have nitrate, sulfate, carbonate, phosphate, and so on, okay? Perhaps in my class, you've written these on the back of a periodic table. If not, you want to do that ASAP, so you have a common listing of those. All right, let's practice some dissolution for molecules, ions, that are polyatomic now, okay? So we have sodium carbonate. When this dissolves, it forms sodium ion. We know that's a +1 charge. And then carbonate, recognize carbonate as a grouping. That's always CO3 2-, okay? Then don't forget to balance the chemical equation. Now we use the 2 by the sodium to put a 2 in front of the sodium on the right. How about this Ba parenthesis OH2 thingy? Well, that's barium hydroxide. Barium we saw before is in group 2, so it has a +2 charge. And this thingy is OH-. That's a polyatomic ion called hydroxide. Please memorize that. And now we use the subscripts to balance this chemical equation on the right. We put a 2 in front of the hydroxide. This next one is hopelessly complex. It's aluminum sulfate, okay? Or aluminium sulfate, if you're watching this video in a country that pronounces the element aluminum correctly. So we got aluminum in group 3 of the periodic table. It has a +3 charge. And then this SO4 thing with the parentheses, pull one of them out. It's inside the parentheses. And remember that has a -2 charge. Please remember or memorize that sulfate is -2. It's SO4 -2. Now we want to balance the equation here. So we've got a 2 for the aluminium ion. So make sure you put a 2 in front of that. And we've got a 3 for the sulfate ion. So put a 3 in front of the sulfate. All right. So that's your balanced chemical equation there. All right, now let's switch gears to the second type of substances that will dissolve in water, and these are called molecular compounds. Now, molecules do not dissociate or break apart to form ions because they're not made of ions. For example, look at the structure sugar here, okay? This is glucose, C6H12O6. There are no metals in this formula. It's only comprised of nonmetals, which means there's no ions in this. It's all held together by covalent bonds. If we were crazy, we could draw a little structure of that, okay? When this substance dissolves in water, it forms aqueous C6H12O6 molecules, and there will be a bunch of water molecules surrounding each glucose molecule in solution, and we indicate that as AQ. Another homogeneous solution can be made from ethanol. Now, ethanol is a liquid in its pure state, but when it's dumped into water and stirred, it becomes homogeneous, and we form C2H5OH AQ. So all we're doing is keeping the formula exactly the same, and we're changing the state, either solid or liquid or maybe even gas, to AQ. How about oxygen? We know fish, for example, can breathe underwater somehow. There must be oxygen in the water. Well, O2 gas forms O2 aqueous, okay? And that's the chemical equation there that describes oxygen dissolving in water. All of these are molecular compounds. Please don't break apart the O's and the H's and the C's and stuff from each other. Thanks for watching. Please like, please subscribe. Have a great day, everybody.